Hello. This video is about infinite limits. And by that I don't mean limits as x approaches infinity, but rather when you have the limit as x approaches some number of some function, but that limit turns out to be infinite. So let's start off with a question. Can we say that 1 divided by 0 equals infinity? You probably know that we can't divide by 0. Division by 0 is undefined, but why? Why can't we just say that if you take a number and you divide by 0, you get an answer, and that answer is infinity? So can we say that 1 over 0 or 1 divided by 0 is infinity? If no, why not? And if yes, what does it mean to say that? Well, I'll go ahead and give you the short answer now. There are two problems with saying that 1 divided by 0 is infinity. One problem is that infinity is not a number. To be precise, it's not a real number. It's not part of the set of real numbers, which is what we work with in basic calculus. There are number systems that do include infinity or infinities, but if you try to treat infinity as a number, then that messes up some of the things that you do with numbers. Some of the things that you want to do with numbers don't always work the way you would expect. The other problem is that if you have 1 over something that is close to 0, that might come out positive or it might come out negative, because numbers that are close to 0 include numbers that are a little bit less than 0, as well as numbers that are a little bit greater than 0. However, we can talk about what happens when you divide by a number that is close to 0. So we can talk about that by talking about the limit as the denominator approaches 0. So that's what we're going to be looking at in this video. So consider this example. Take the function f of x equals 1 over x squared. And think about what happens when x is a very small number. Not quite 0, but really close to it. For a really small number, like 1, or 1/2, or 1/10, or 1/100th, or 1/1,000,000th, x squared, x times x, is going to be even smaller. 1/2 squared is 1/4. 1/10 squared is 1/100th. 1/1,000,000th squared is 1/1,000,000,000th. So the closer x is to 0, the smaller x squared is, and then the smaller a number you divide by, the bigger a quotient you get. So the smaller the denominator is, the larger 1 over that denominator is. So if x is a small number, x squared is a small number, and 1 over x squared is going to be a very large number. If x is 1/10 or 0.1, 1 over x squared is 100. If x is 1,000th or 0.001, 1 over x squared is 1,000,000. And this still applies if x itself is a negative number, because x squared is still going to be positive, and then 1 over x squared is still going to be positive, and the closer x is to 0, the larger that positive 1 over x squared is going to be. And you can see that on the graph. Points on the graph that have x coordinates that are really close to 0 have y coordinates that are way up there. So what we can say in a situation like this is that the limit as x approaches 0 of this function 1 over x squared equals infinity. And when we say that the limit equals infinity, we are not saying that the limit exists and that's what it is. Rather, we are saying that the limit does not exist, but we're explaining or being more specific about why it doesn't exist. It doesn't exist because the values of that function get arbitrarily large when x is close to 0. Values of 1 over x squared increase without bound. There's no limit or boundary to how big they can get as x gets close to 0. Pick any number, no matter how large. 1,000,000, 1,000,000,000, 1,000,000,000,000, a sextillion. I can find values of 1 over x squared that are even bigger than that just by making sure that the number I put in for x is close enough to 0. If you're interested in the formal mathematical definition, you might want to think about how you would modify the definition of the limit being some number to talk about what happens when the limit equals infinity. Here's what that would look like, in case you care. And if you don't care, you can ignore this. But to say that the limit as x approaches c of f of x equals infinity means that for every number m greater than 0, no matter how large, there exists a number delta greater than 0 such that f of x is greater than m whenever 0 is less than the absolute value of x minus c is less than delta. So that means that for any number you pick, no matter how large, m could be 1,000,000 or 1,000,000,000 or a sextillion, I can get values of f of x to be greater than that number just by making sure x is close enough to the number that it's approaching, c. Now here's another example. Here the function we're looking at, f of x equals -3 over x squared. And this time, when we plug in a number for x, whether x is positive or negative, x squared is going to be positive, but then -3 divided by x squared is going to come out negative. So the smaller x is, or the closer to 0 x is, the larger in absolute value -3 over x squared is going to be, but it's going to be negative, and it's going to be more negative the closer x gets to 0. So if I put in either positive or negative 1,000 for x, x squared would be positive 1/1,000,000th, and then -3 divided by 1/1,000,000th would be -3,000,000. It would be way down there. So on the graph, the points that have x coordinates close to 0 have y coordinates that are way down there off towards -infinity. And so we can say that the limit as x approaches 0 of this function, -3 over x squared, is -infinity. Again, that doesn't mean the limit exists. That means the limit does not exist because the values of that function get arbitrarily small. That is, large in absolute value, but negative when x is close to 0. And then what about just plain old 1 over x? Well, this time, if we take x to be a number that's close to 0, numbers that are close to 0 include positive numbers like positive 1/1000th, as well as negative numbers like -1/1000th. And if x is positive, 1 over x is going to be a big positive number. If x is negative, 1 over x is going to be a negative number. So on one side of 0, we get the graph going way up, and on the other side, we get the graph going way down. So we can say the limit as x approaches 0 from the right is infinity, that is positive infinity. The limit as x approaches 0 from the left is negative infinity. And if we just had the limit as x approaches 0 without specifying which side, all we can say is that the limit just doesn't exist. So I could say 1 over 0 equals plus or minus infinity. And that's not really a precise, well-defined mathematical statement. That's really more a way of just remembering what's going on when you have something on top over something on the bottom that's going to 0. So what I mean by that is, as a general rule, if you have a fractional expression, a quotient, a function that's in the form of something over something else, if the denominator approaches 0 while the numerator does not approach 0, I've already said in a situation like that, that's enough to be able to say the limit doesn't exist. But now I'm just being a little bit more specific. I'm saying you can say either the limit is infinity, or the limit is negative infinity, or some of both. Like in that last example where it's positive infinity on one side and negative infinity on the other side. So to tell which it is, you need to think about whether you get values of the function that are positive or negative. So consider the function x minus 13 over x minus 9, and what happens to that as we let x approach 9, either from the right or from the left, or from both sides. So if x is approaching 9, this numerator would be approaching 9 minus 13, which would be negative 4. And the denominator would be approaching 9 minus 9, which would be 0. So we do have a situation where the denominator approaches 0 and the numerator does not. And we could just say, okay, these limits don't exist. That would be perfectly true. But let's be a little bit more specific and say a little bit more about what they're doing that makes them not exist. So in this first case, think about what happens when x is approaching 9 from the right. So now we're considering x's that are a little bit greater than 9. If you take a number that's a little bit bigger than 9 and subtract 13, you're going to get something that is still close to negative 4. And so it's definitely going to be negative. All the numbers that are anywhere close to negative 4 are all negative numbers. Now look at the denominator. If you take a number that's a little bit bigger than 9, and then you subtract 9 itself, you are going to get something positive. Like, for example, 9.1 minus 9 is 0.1. So if x is bigger than 9 by even a little bit, x minus 9 is positive. And when we have a negative number on top divided by a positive number on the bottom, that comes out negative. Negative divided by positive is negative. So the limit is negative infinity. Now what about the limit as x approaches 9 from the left? The numerator is still close to negative 4, so it is negative. And this time the denominator comes out negative because we're taking a number that's a little bit less than 9 and subtracting 9. Something like, for example, 8.9 minus 9, which would be negative 0.1. So we have negative on top divided by negative on the bottom, which is positive, and so we can say that limit is positive infinity. And then if we just say, what's the limit as x approaches 9, all we can say there is it does not exist. It would be negative infinity on one side, positive infinity on the other side. And here's what the graph looks like, but I wanted you to be able to figure that out from the formula, from analyzing the function itself, before you look at the graph. But notice how the graph agrees with what we said over here. If x is on the right of 9, but approaching 9, the graph is headed downward. If x is to the left of 9, but approaching 9, the graph is headed upward. What's the limit as x approaches -1 from the left of the function x over x plus 1? So we have a numerator that is approaching -1. We have a denominator that is approaching -1 plus 1, which is 0. So we have that situation where the denominator approaches 0 and the numerator doesn't. So this limit might be infinity, might be negative infinity. Let's think about whether the numerator and denominator are positive or negative as x approaches -1 from the left. So as long as x is close to -1, that numerator is close to -1, which makes it negative. And what about the denominator? Well, here we're taking a number that's a little bit less than -1. And remember, numbers that are less than -1 would be numbers to the left of -1 on the number line. Things like -2, -3, -1.01. But if we take one of those numbers and add 1 to it, we get something that is still negative. It's still less than 0. So we have a negative numerator over a negative denominator. Negative divided by negative is positive, and so we can say that the limit is positive infinity. So look at the graph. Here's where x is -1. If we are approaching -1 from the left, the graph is headed upwards towards positive infinity. What about this one? What is the limit as x approaches pi from the right of the function cosecant of x? First of all, remember that the cosecant function is the reciprocal of the sine function. So it might be easier to think about it as 1 over sine x. And now we have a numerator that is just 1, and a denominator that is approaching the sine of pi, which would be 0. So we do have that situation where the denominator is approaching 0 and the numerator isn't. And if x is greater than pi, approaching pi from the right, so we're thinking about numbers that are a little bit bigger than pi, is sine positive or negative? Well, an angle that is greater than pi by a little bit is down in the third quadrant. And in quadrant 3, sine is negative. So we have a positive numerator over a negative denominator. That makes it come out negative, and so that limit is negative infinity. And you can see that on the graph. Here's the graph of cosecant x, or 1 over sine x, and as x approaches pi here from the right, so we're looking at points on the graph with x coordinates that are just a little bit to the right of pi, the graph is headed downwards towards negative infinity. And one more example, the limit of the function natural logarithm of x, the ln of x, as x approaches 0 from the right, is negative infinity. You cannot take the logarithm of 0, but you can take the logarithm of a number that's just a little bit greater than 0. And so the natural logarithm of a number that's just a little bit bigger than 0 is a very negative number. It's large in absolute value, but it's negative. So the closer x gets to 0, the more negative ln of x becomes. All these examples we've been looking at, the graph has been shooting either way up or way down, or maybe both. And so we can say that the graph is asymptotic to a vertical line, or that it has a vertical asymptote. So in general, an asymptote is a straight line that a curve approaches. If a curve, like the graph of a function, seems to be straightening out and getting more and more like a particular straight line, that line is an asymptote for that graph. And in particular, whenever you look at the limit as x approaches some particular number, c, either from the right or from the left or both, if that limit turns out to be infinite, if it's either positive infinity or negative infinity, or one of those on one side and one on the other, then the graph of that function has a vertical asymptote x equal to that number c. So looking at the examples we've already seen, the function 1 over x squared has a vertical asymptote right here. It's the y-axis, the line x equals 0, because the limit as x approaches 0 is infinity. So no matter how far out we zoom the graph, this graph will never quite touch the y-axis, but it will get very, very close to it. And as it gets closer and closer to it, it's looking more and more like it's just going straight up the way the y-axis does. It never quite completely straightens out or completely touches the y-axis, but it gets very, very close to it. Also, the function negative 3 over x squared has the y-axis as a vertical asymptote. And so does the function 1 over x. In each case, the limit as x approaches 0 is infinite, and so as the points on the graph get closer and closer to 0 in the x direction, they go way up or way down in the y direction. And they straighten out, never completely, but they look more and more like that straight line x equals 0, otherwise known as the y-axis. Same thing with the natural logarithm function. It also has the y-axis as a vertical asymptote. And then the function x minus 13 over x minus 9, remember there we were looking at the limit as x approaches 9, either from the right or from the left or both. That limit turned out to be infinite, and so the vertical line x equals 9, shown here as a pink dashed line, is a vertical asymptote for that graph. If I zoom way out, the graph is never going to quite touch that line, but it's going to get very, very close to it. And the function x over x plus 1, there we were looking at the limit as x approaches negative 1 from the left. That limit turned out to be infinity, and that tells us that that line, x equals negative 1, is a vertical asymptote for that graph. That graph is asymptotic to that straight line. And the cosecant function has the line x equals pi as a vertical asymptote. It also has other vertical asymptotes, including x equals 0, x equals negative pi, x equals 2 pi, and really x equal to any integer multiple of pi. Now, what about the function f of x equals x squared minus 4 over x squared minus 7x plus 10? Can you tell what, if any, vertical asymptotes the graph of that function would have before we just go ahead and look at the graph? See if we can figure out where it would have vertical asymptotes. It would help to factor the numerator and the denominator. The numerator is a difference of squares. It factors into x plus 2 times x minus 2. And the denominator factors into x minus 2 times x minus 5. So you can see that the denominator would be 0 when x is either 2 or 5. So those are places where we could possibly have a vertical asymptote. So we want to look at what's the limit as x approaches 2 and as x approaches 5, and is either one of those limits infinite? Well, the limit as x approaches 2, we have a common factor of x minus 2 in the numerator and in the denominator, which we can divide out, and then the limit as x approaches 2 would be, well, we've got a numerator approaching 2 plus 2, a denominator approaching 2 minus 5, and so the limit is negative 4/3. So that limit is not infinite, and so we do not have a vertical asymptote x equals 2. But if we look at the limit as x equals 5, we could break it down into the limit as x approaches 5 from the left and then from the right. So if x is a little bit less than 5, both factors on top are positive. X minus 2 would be close to 5 minus 2, which is a positive 3. But x minus 5, you have a number that's a little bit less than 5 minus 5 itself. That comes out negative. So on top, positive times positive is positive. On the bottom, positive times negative is negative. And then a positive divided by a negative is negative. So that limit is negative infinity. As x approaches 5 from the right, now we're looking at x's that are a little bit greater than 5, and all of those factors individually are positive. And so the whole thing comes out positive, and as x gets closer and closer to 5, that just gets larger and larger. That limit is positive infinity. So here's what the graph looks like. There is actually a missing point there where x is 2, but you can't tell from the graph that it's missing because all the other nearby points are there. And the limit exists. The limit is negative 4/3. But there is a vertical asymptote here. It's the line x equals 5. And as x approaches 5 from the left, the limit is negative infinity. As x approaches 5 from the right, the limit is positive infinity. So the line x equals 5 is a vertical asymptote, but x equal to 2 is not. So that's infinite limits. Thanks for watching.